There's a simple way to drop the temperature of your home by up to 25 degrees Fahrenheit, and it costs no more than a few clay pots and a trickle of water. This cooling system outperforms modern air conditioning in extreme heat, consumes 80% less energy, and requires no chemical refrigerants, compressors, or complex electronics. Yet, while the $100 billion HVAC industry sells us plastic boxes that cost thousands to install and hundreds each month to run, this technology remains virtually unknown to most of us. So what is it? How does it work? And more importantly, why are we not using it? Let's find out. To understand the brilliance of this system, we must look at the arid, blistering plateaus of ancient Persia and the sun-drenched courtyards of Egypt. Thousands of years ago, survival in these landscapes wasn't a matter of comfort, but biological necessity. Builders here faced a fundamental crisis: how to keep a city habitable when the ambient temperature regularly exceeds 113 degrees Fahrenheit. The solution they found wasn't a machine, but a material. They discovered that unglazed, porous earthenware jars, when filled with water and placed in the path of a prevailing breeze, didn't just hold liquid, they cooled the air around them. This revelation led to the birth of the mashrabiyah in the Middle East and the jali in India, ornate, perforated screens that used the physical properties of earth and wind to cool entire palaces long before the advent of the electrical grid. By 400 BC, the Persians had scaled this logic into the yakhchal, massive mud brick domes reaching 59 feet into the sky. These structures were sophisticated refrigerators that used subterranean pools and wind catchers to manufacture and preserve ice in the middle of a desert summer. This technology eventually migrated into the Indian subcontinent, where it was adopted and expanded upon by the Mughal emperors. During the 16th and 17th centuries, the Mughals engineered the Abdar Khana, or the water house, and the Baraf Khana, the ice house. These were not mere storage rooms, but active thermal systems using sandstone cisterns and insulated cellars. Emperor Akbar famously organized a massive relay system to transport ice from the Himalayas to the plains of Delhi, but it was the domestic production, using shallow ice pans and straw-lined pits, that proved how effectively terracotta and earth could manipulate temperature. These historical precedents established that cooling with mud and water is not a new or alternative innovation. It is the rediscovery of a resilient technological heritage that was systematically marginalized by the 20th century advent of chemical refrigerants. The modern revival of this lost knowledge arrived in 2017 with the invention of the Beehive terracotta cooler. Manish Siriparapu, an architect in New Delhi, was faced with a crisis at a local electronics factory where the exhaust from a massive generator was creating a 50-degree heat island that traditional air conditioning could not touch. He realized that the ancient geometry of the beehive, a shape that maximizes surface area in the smallest possible footprint, could be combined with traditional claycraft to solve a modern industrial problem. The beehive cooler works because of a single law of physics. When water evaporates, it must consume heat to change from a liquid into a gas. In this system, that heat is stripped directly from the air. This is what is known as evaporative cooling. To understand how this happens, you have to look at the clay itself. Unglazed terracotta is a porous material filled with millions of microscopic channels. When the stack is wetted, these channels act like a network of tiny pipes, pulling water from the reservoir and moving it through the entire body of the clay until every surface is saturated. This is called capillary action, and it ensures that the cooler is always covered in a thin, consistent film of moisture. The beehive geometry is what transforms this from a simple wet pot into a high-performance cooling engine. If you just used a flat wet wall, the air would bounce off the surface without losing much heat. But by stacking hundreds of terracotta tubes into a honeycomb, you create an immense amount of surface area in a very small space. As the hot outside air is pulled into these tubes, the circular shape forces it into a tight, spinning motion. This turbulence ensures that every molecule of air is forced to strike the wet walls of the clay. At the moment of impact, the water on the clay surface steals the thermal energy from the air to fuel its own evaporation. But there's another clever phenomenon this design utilizes called the Venturi effect. Because the air is being squeezed into narrow openings, its velocity increases. This faster-moving air causes the water to evaporate much more quickly, which in turn drops the temperature of the air even further. By the time the air reaches the other side of the stack, it has been stripped of its heat and arrives in the room as a dense, chilled breeze that can be up to 27 degrees Fahrenheit, colder than the environment outside. And in that electronics factory in Noida, this stack of clay achieved what traditional mechanical cooling could not. It dropped the temperature from a blistering 122 degrees down to a manageable 97 degrees Fahrenheit. But the success of the system isn't just measured by a thermometer. Unlike a standard air conditioner, which strips moisture from the air and leaves it feeling dry and stale, the beehive cooler filters the air and adds a natural, gentle humidity. This process creates a phenomenon known as petrichor, the distinct earthy scent produced when rain falls on dry soil. And this isn't just a pleasant side effect, it has a documented psychological impact on the human brain. When we smell petrichor, our perception of heat drops even further than the sensors on the wall suggest, providing a deep sense of relief that a plastic chemical unit cannot replicate. The energy data from the Noida project revealed the true scale of this efficiency. To cool an industrial space of that size, a conventional mechanical air conditioning system would have consumed massive amounts of electricity. The Beehive system, however, performed the same task with a measured 80% reduction in energy consumption. The entire installation ran on less than 0.63 units of energy per hour. It provided industrial strength cooling for less than the cost of running a few household light bulbs. In a world of rising energy costs and an unreliable electrical grid, this project proved that we can achieve modern comfort while bypassing the expensive, grid-dependent systems we've been told are mandatory. But if this technology was so good, why isn't it the standard for every home in the United States? The most obvious reason is that it isn't an effective solution for many homes that aren't built in the right climate. Evaporative cooling is much less effective in humid climates because high ambient moisture limits water evaporation, or in climates that have both extreme temperature fluctuations across both summer and winter. A permanent open structure design like this will require very clever solutions to reduce heat loss in the colder months. In these places, mechanical heating systems are a logical choice. But there are plenty of homes located within the Sun Belt where the Beehive structure would prove to be a powerful passive cooling system. And for these homes, the barrier is less about instability and more about the way our economy is structured. The global cooling market is dominated by a handful of massive corporations that rely on a cycle of high-margin sales and planned obsolescence. An air conditioning unit is a complex machine with hundreds of moving parts, designed to be serviced annually and replaced entirely every 10 to 15 years. There is no recurring revenue in a stack of clay pots that can last for half a century. You cannot sell someone a technology that they can build themselves from the earth beneath their feet, so the industry simply ignores it. And in the United States, this system is safeguarded by our rigid building codes. For the last 50 years, American homes have been designed as airtight, plastic-wrapped boxes. Our regulations are written around the sealed envelope model, which requires mechanical ventilation to keep the air breathable. The Beehive cooler, on the other hand, is a breathing system. It requires a constant exchange of air with the outside environment to function. Because it doesn't fit into the standardized efficiency ratings used by building inspectors, it is often legally excluded from primary residences before the first brick is even laid. Developers and landlords also have little interest in solutions like this, as they will often just choose the cheapest cooling system to install, the standard electric AC unit, because they aren't the ones paying the monthly utility bills. The tenant bears the cost of the electricity, while the landlord avoids the effort of integrating a more efficient, unconventional system like the Beehive. We are stuck with a technology that is expensive to run and bad for the planet, not because it is the best solution, but because it is the most profitable or convenient one for the people who build or sell our houses. But you can reclaim this technology today without waiting for a commercial product to reach your local big box store. Because the physics of the Beehive cooler are open source, the barrier to entry is remarkably low. If you want to build a functional unit this weekend, the most accessible route is the flower pot method. You must source unglazed terracotta, either pipes or standard garden pots. The unglazed property is vital. If the clay is fired with a decorative sheen, the microscopic pores are sealed, and the water cannot migrate to the surface to facilitate cooling. To assemble your stack, you arrange these pots in a honeycomb pattern within a simple wooden or metal frame. This geometry ensures that as air is pulled through the centers, it is compressed and forced to interact with the wet clay. And if you want to automate the system, you place a small 12-volt fountain pump in a reservoir at the base and run a plastic manifold to the top. This pump slowly drips water over the stack, keeping the clay saturated. By connecting this pump to a small 20-watt solar panel, you create a self-regulating machine. As the sun gets hotter, the pump works harder and the cooling increases exactly when you need it most. But for those looking for a more professional or industrial scale installation, Ant Studio in New Delhi, led by Monish Sirpurapu, offers specialized design services. They have evolved the beehive from a single factory experiment into a modular system that can be integrated into the facades of large buildings. While they are based in India, their work has sparked a global movement of architects and makers who are adapting these terracotta modules for different climates. If you're looking for hands-on training to master the integration of these systems into sustainable architecture, organizations like the Center for Science and Environment in India and various permaculture institutes in the United States and Europe provide workshops on passive cooling and vernacular building techniques. The Beehive Cooler is a 4,000-year-old answer to a modern problem. It shows us that we don't have to be trapped by the power grid to stay comfortable in a hot world. By using the way water moves through porous clay to soak up heat, we can cool a home for the price of a few garden pots and a small solar pump. A lot of the solutions we talk about were marginalized because they weren't profitable enough to sell. If you find this knowledge valuable, then subscribing and sharing is the best way to make sure it doesn't disappear again.